Okay, so as you can see from here, uh, today we'll be learning magnetic field due to a current element. Okay, we'll learn what is current element and how to calculate magnetic field for a current element, given current element, and that is viewed by the use of Savarts law. Excuse me. This is by the use of Savarts law. So let us first learn what is Savarts law. I hope you people are able to see my screen. So this is the title for the for today's topic. So let me go to my presentation. Okay, so we'll first learn Savarts law. Okay, so look, Savarts law actually helps us to find out magnetic field. Like say in case of electrostatics, we have learned Gauss's law. Okay, Gauss's law for calculating electric field, etc. Okay, for various geometry. Okay, so here Gauss's law is obviously there in magnetostatics, but in this case, when I am talking about a current element or a current carrying wire, so how much magnetic field will be created by a current carrying wire at certain distance? So that can be calculated using few laws here. The first law is actually Biot-Savart law, as you have seen, Biot-Savart law. So this law we are going to learn today. Then further we'll be seeing Ampere's circuital law. These two are fundamental. Ampere's circuital law. Basically, these two laws will be using everywhere to calculate magnetic field due to a current carrying wire. Okay, so current carrying wire can be of any shape, any size. Okay, so today we'll see how what is Biot-Savart law and how do we use this Biot-Savart law to calculate magnetic field for a current carrying loop, circular loop. Okay, so these two topics we'll try to cover, and then we'll take a few numerical examples if time permits. So let us see what Biot-Savart law says. As such, Biot-Savart law does not have like proper statement or something like that to say. So here you look, suppose there is a X, Y. This is a conducting wire. Okay, conducting wire. Conducting wire. What is that? Conducting wire. It is carrying a steady current. Okay, carrying a steady current. What is that current? Steady current. Steady current means it does not have any variation with time as well as at space. Okay, it does not have any variation with respect to time or with respect to space. So this is a steady current. All right. Now, if I have been given a such kind of wire, can I calculate magnetic field at any point? Okay, at any point around this wire. Okay, so here a representative point P is taken here. Okay, so this, suppose this is a point P, and due to this wire, whether I can calculate the magnetic field. What is the magnetic field creates? As you know, that current carrying wire creates a magnetic field around it. So magnetic field around it. So what is that? So that we know already. that it will create a magnetic field, but quantitatively whether I can find out the magnitude of the magnetic field as well as the direction of the magnetic field at any point from this wire, whether it is right side, left side, or anywhere. Okay, around near to this wire. So Biot-Savart law will help us to do that. Let us let me tell you first about this figure itself. Look this figure. So steady current is flowing. So this is XY. This see dot lines are there, right? Dotted lines are there at the end of this XY. That means this current carrying wire can be infinite, of infinite length. Okay, it can be of infinite length, or even it can be of finite length. Just a minute, I am getting an urgent call. I'll be back in a minute. Yeah, I'm sorry. I had to attend one urgent call. So uh, I was talking about this current carrying wire. This is an infinite length, or it can be finite also. So it can be applicable for both actually. We'll see that. And look, there is a steady current as I told already. It is flowing through this wire. Now I have to calculate the magnetic field over here. So according to Biot-Savart law, so what Biot-Savart law says that magnetic field at any point P, suppose this is a point P, so this can be, if I just take an element means, see, I have infinite length, right, or finite whatever. So I have a bigger length. So what I can do, I can just take a small element of this length element of the wire. Okay, so I have a wire like this. So I can take a small part of it, which is called element of the wire, and this I'm telling as DL, what they have written here. And look, as I told already, that the direction of this DL will be in the direction of the current or tangent to this. Okay, at any point it is actually tangency. You can see this tangent. So this tangent will be the direction. So this will give you the direction, and obviously you have to take the tangent along the direction of the current. So your current is flowing this way. So see, if you look carefully in your book, so this is a small arrow. Okay, so faint blue or light blue arrow, this part. This is called element, and when I multiply this length with the current, okay, length of this element with the current, this is called current element. What is this called? Current element. Current element. Okay, we'll see in case of this. In case of uh, magnetic field, so the source of magnetic field is actually this current element. Okay, in this case, source of magnetic field at this particular point is the current element. So when you multiply this length of this element with the current, then it is called current element. Ideal. Now look, the direction, as I said, the direction of the current element will be in the direction. So you have to draw a tangent at any point. If you take here, you have to draw a tangent like this, and you have to take the direction of this in this way, along the direction of the current. Okay, like that you have to take the element. Now I have got the element. Now look, this distance from the wire up to this point P, where I have to calculate the magnetic field due to this small element is called R. This distance is called R. Sometimes it is called radius vector also. Okay, and look, the angle between this this current element, is the tangent I have taken, and up to this R vector. So this is angle between, so theta actually angle between ideal vector and this R vector. So the angle between this, okay, theta is angle between this. So according to Biot-Savart law, at any distance from the current element, if you want to calculate the magnetic field, suppose for this ideal element, current element, the magnetic field, okay, magnitude of the magnetic field actually directly proportional to the current element, ideal, and it is inversely proportional to the square of the distance, very much similar to your Coulomb's law. Okay, inversely proportional to the square of the distance between the wire and the point where you want to calculate the magnetic field. So I can say this is a test point and this is the source. So this R is the distance between the test and source of the magnetic field and the point of test. Okay, where we are trying to calculate the magnetic field. Okay, so uh, this proportionality, if I combine together and write the vectorial form of this Savarts law, vectorial form. So what I can write is I dl cross r divided by r cube. Okay, so this is the vectorial form of this uh, of the Savarts law. Okay, if you have been already given a straight wire, if the length is given, in place of dl you can write exactly il. Okay, then I can write il cross r. So if you want to calculate at any point r here, so il cross r by r cube. So I'll request you to remember Savarts law in terms of this vector. Don't go for remembering the scalar form. Okay, so which I'll be writing now. So this is the vectorial form or vector form of the Savarts law. If I want to calculate or know the magnitude of this, so this I can write I dl by r square into sine theta. As you know, this dl and r, dl cross r, this is a cross product, and the angle between these two is theta. So I can write according to the rule of cross product, it will be a sine theta. Okay, it will be sine theta. I dl by r square into sine theta. Don't remember this alone because this is a uh, this is this will give you the magnitude, but you will be misled while calculating or finding out the direction. Okay, so you might be thinking, so how to find out the direction of the magnetic field? So look here, I don't know whether you remember, I have told you a right hand thumb rule. If the current is flowing in this way, so the magnetic field lines will be, actually you can place your thumb like this, okay, and curl the wire like this. Okay, so then the tip of your finger would give you the direction of the magnetic field. Okay, like this, in this case, like this, like this. Okay, so in this case, look, if I talk about this point P, how the magnetic field lines are, like whether the magnetic field is going into the phase or coming out of the phase. So here obviously you can see the magnetic field at this point. If you just apply your right hand thumb rule, you will correctly get the direction of the magnetic field, that it is going into the phase plane of the paper. Okay, and if I would have asked you to calculate the magnetic field at some point here, so at this point, look, the magnetic field lines will be coming out of the page. So here it will be coming out of the page like this. Okay, here it is going into the page, here it is coming out of the page. So you have to exactly use your thumb rule, right hand thumb rule, to get the direction of the magnetic field. Okay, so this is actually Savarts law. Now you might be thinking, sir, I have got only for the element. So how do I get for the whole wire? If it is a finite wire, if it is infinite wire. So if it is a finite wire, look how can I get? See, this Savarts law also follows principle of superposition. What it follows? Principle of superposition. I don't know whether you remember from your first chapter. Principle of superposition. Okay. So suppose you have a extended wire like this, a long wire, you want to calculate the magnetic field for the whole length at this point, okay, at this point P. So what you can do, you can take small element, you can divide small element and calculate the magnetic field for all the elements, and then you sum them up, okay, sum them up. Suppose this goes from 1 to n if it is a finite wire, okay. So you will look, so this r is constant, it does not change, okay, more or less it is constant, okay. So what I can write, I can write here only this dl. If you take the summation over dl, you get the magnetic field for all whole the wire, okay. So now we will look in your book, we will see there are few similarities and dissimilarities between the law, this Savarts law, and the Coulomb's law, which we have already learnt in our previous section, okay. Okay, so before I go there, look this, if I just uh, make this as equation, okay, if I make this as an equation, so proportionality constant comes as mu naught by 4 pi. You can see this, it is mu naught by 4 pi, and this mu naught by 4 pi has a value, you can see mu naught by 4 pi has a value in SI unit as 10 to the power minus 7 Tesla meter per ampere. So this unit you can find out from this equation, okay. So this is actually magnetic field has unit Tesla. You can see this is, so if you just make it a, like if you just get the magnitude, so this will be ideal by r square. So this is your r square means meter, so Tesla meter square divided by ideal, so ampere into meter again, so you'll get this unit, okay, if you just come from here, okay. So this is what, so this mu naught is called actually the permeability of free space or vacuum. Permeability, what do you mean by permeability? Actually permeability, so this mu actually called permeability, and mu naught is actually permeability in free space or vacuum, if you say, okay. So permeability means what, if I suppose have a material like this is a material which can be magnetized, okay. So it has certain amount of permeability, suppose say mu is equal to 5, suppose, and this is a dimensionless quantity again. Sorry, mu r, relative permeability. This is a relative permeability, this is similar to this again, mu is equal to mu naught into mu r, and mu r is equal to mu by mu naught. So this is permeability inside a material, okay, any material, suppose this is a material, and relative permeability is the ratio of the permeability of the material to the permeability in the vacuum. So this will give you the relative permeability. This mu r called relative permeability, just like your relative permittivity in electrostatics, okay. So what does this mean? Suppose I have external magnetic field, so this is not magnetized, suppose non magnetized first, okay. So sorry, this is 0, so this is non magnetized bar, okay, non magnetic bar. So if I want to make a magnet, like induce magnetism in this, I have to apply external magnetic field, okay, external magnetic field. So field lines will go like this, suppose, okay, they are coming like this. So I'm keeping inside the magnetic field, applied external magnetic field. So permeability will actually determine how many field lines penetrate through So these are external field lines. So penetrate through this material. How many? If it is 5, then there will be 5 field lines penetrating this material or going through the material. All others will go out of that. Okay, out of the material. All others will go out of the material. So permeability, so permission, given permission. Okay, so that in that sense it is permeability. Okay, how many field lines it can permit. Okay, so this is the case here. All right, so this is called permeability. Okay, so let us go to Coulomb's law. See, Coulomb's law, we know Coulomb's force, like Q1, Q2 by 4 pi epsilon naught and R square. You look, this Savarts law, what it is saying, I L cross B. Okay, if I take vector, so it will be radially outward. Let us see that. And this is, sorry, this is R by R cube. Okay. Look, these two forces will compare these two. This is Coulomb's law and this is Savarts law. So these two are actually similar in this way. See, both cases, if I take the magnitude, you will see it will be actually will be proportional to 1 by R square only. And in this case also, force between two charges are actually inversely proportional to the square of the distance. Okay. And look here, the source for this force actually is the electric field created by the charges, or I can say the source for this force is actually the charges. Okay, charges Q1 or Q2. If I take one of them unit charge, then it is a charge. Okay, so the source for electric force field, electrostatic force field is the charge, point charge. But in this case, you look, this is I into L. This is a current element or current carrying wire or a loop. Okay, this is IL. This is current element. The source for the magnetic field is current element. Now look the direction. If I have two charges, Q1 and Q2 here. So the force by, if I write this is F21, force, both are positive, right? So force on Q2 by Q1 will be a repulsive force. So this will be in this direction, okay? As I have shown. So this is actually in the direction along the line joining the charges, okay? Point charges. Along the line joining the point charges. But what about this? What is the direction? Direction of force loop, this is actually the L, IL, this and this. And the cross product of this will give you the direction. What does it mean? It means that the direction of B will be in the direction perpendicular to the plane containing L and R. IL suppose this way, R is this way, so it will be perpendicular to this plane. Okay, containing these two. Exactly, because of the cross product, you get magnetic field direction in the completely opposite plane. Completely, the plane in the plane perpendicular to the plane where IL current element and R is situated. Okay, this is the difference, and few more differences we can find out. So one more is actually look here. So as I have already told the source is charge here, current element, the distance, the direction. Okay, direction. One more important point is here, which we will be learning again here. Look in a book. One more important uh, difference is actually, yes. So the Coulomb force does not depend on the angle between the charges, but in this case, it depends on the angle between the current element and the radius vector. So this is another point, okay, which you'll see. So there are few things here, positive, like the similarities and dissimilarities between Coulomb's law in electrostatics and Savarts law in case of magnetism. So you just read these points, okay. So I think I have discussed those things. And one important point is, see the relation between mu naught and epsilon naught. If there is an interesting relationship between them, which we'll be learning again in uh, in the 8th chapter, where we'll be discussing the electromagnetic theory. Okay, so look here. So in case of electromagnetic wave or electromagnetic theory, we'll be learning again what is the relation between mu naught and epsilon naught. But for the timing, we'll just tell you what it is. So mu naught we know SI unit is actually the SI unit is mu naught by 4 pi, or this way also you can write mu naught by 4 pi. You can write as 10 to the power minus 7, as you know, 10 to the power minus 7. You can take appropriate unit. Okay. Now you know 1 by 4 pi epsilon naught, right? 1 by 4 pi epsilon naught is actually that gives you 10 to the power 9, right? With the proper unit. I'm not taking because this unit, if I take the ratio, they will obviously some adjustment will be there, and see what I'm trying to show you the value exactly, the what is the magnitude of this value, and you will be appreciating this. So let us take uh, mu naught, okay, and we'll take epsilon naught like this, okay. Now look, I'll do one thing. So I'll just multiply 4 pi here, 4 pi by mu naught, okay, and I'll multiply 4 pi down again, 4 pi epsilon naught. Look, this value, what we know and what we know this for this value. So this is actually, this will be 10 to the power minus 5 here, and this will give you 9 into 10 to the power 9. So if I just take it up, okay, in the numerator, you will get as a whole, this is 16, right? So look here, I can write as 3 into 10 to the power 8 and whole square. So what is this, you know, if suppose this is okay, so what is this value, you know, so far? Suppose this is meter per second, meter per second. What you know this? This is the velocity of light, isn't it? So we have a relation between these two as this, that 1 by mu naught epsilon naught will give you c square. Okay, c square. C is the velocity of light in vacuum. Okay, or in general we write c is equal to velocity is equal to this mu naught epsilon naught. Okay, so this we will learn again during our electromagnetic theory in the 8th chapter. All right. So we have learned the Savarts law. Now let us see whether we can apply this Savarts law for uh, an example. So this example has been taken from your book itself. Look, I know Savarts law, dB, or I can write complete this. If I know the finite length of the wire, if I know, then I can write exactly like this: I L cross B. B is the magnetic field. Oh, I'm sorry. This is IL cross R. This is IL cross R divided by R cube. Okay, this I can write. So applying this formula, let us see whether this problem can be solved. So you look here, the problem says an element DL, is given. So this one is the element, and it has a direction, the direction of current, suppose this way. So that's why they have given the direction also. So this is dx along I cap direction. Okay, along I cap, that means along the x-axis direction. It is placed at the origin and carries a large current of 10 ampere, as you can see from the here figure here. This is the element given, and it is placed at the origin. Now, what is the magnetic field on the y-axis at a distance 0.5 meter? Okay, 0.5 meter distance, and the length of the element is given as 1 centimeter. So this is the point P here. Now, for our case, I have to find out the magnetic field at a distance 0.5 meter along the x direction, sorry, y direction. So let us see how can we apply this formula. So here L is given as delta x, so it has the direction along x-axis, right? So I can write the vectorial form first. So dx, and x cap is given, okay, and this is cross r in the sense this distance, so which is actually along the y direction, right? So some y direction, some value, so this is 0.5, so I can write r means, okay, let us write y into y cap, okay, so this and divided by y cube, like that. Okay, if you just apply in this way, look here, first let me calculate the magnitude itself for this case, then I'll find out the direction. So if I write the magnitude, then I should have written I L R, sorry, R will not be here, then this will be R square, and this will be sine theta, the angle between the element and the radius vector. Okay, radius vector means the distance from the element where I am calculating the uh, magnetic field. So in this case, look, this is the point P. So what is the angle between this? This is x and y. So this angle is 90 degrees. Now theta is 90 degrees. So what I can do, this will be 90 degree into 1, and here the magnetic force, so this magnetic field will be actually maximum at this particular point. So I have got this. Now in place of this, I'll write, look, I already given, okay, so this will be obviously Tesla, in SI unit I'll be writing, so it is ampere, 10 ampere. L is given as 1 centimeter, so which I'll get like this, and R is given 0.5 meter, so I'll write as square of this. Okay, if I do this and do the calculation, then I'll be able to find out the value for this. Okay, so yeah, and what will be the direction? So this value you can calculate by yourself. I'm not doing the whole part, I'm just telling you the direction. If you people have already learned how to apply the thumb rule or the cyclic rules here for the cross product, you know, like cyclic rule I J K, I have told you in the next last class. So you can find out the direction from here. See, I L cross R, I have to find out. So R is here, actually this direction, you look here. So this is y cap, and this is actually dx x cap. Okay, so I basically your cross product is actually with the x cap and a y cap. This cross product, this is a cross product. So you have got the magnitude already. Now you have to find out the direction of the field. So I suppose some value will be here as magnitude, and direction will be this. Okay, what you get from here. So you know, like x and y. So this is x cap means I cap, x cap cross y cap. According to cyclic rule, you'll get from here is actually this magnitude of that and k cap. Okay, or here I am writing x cap y cap, so I should write here z cap, or otherwise you can write I cap j cap k cap, whatever possible. So this maybe you can write as z cap. So it will be along the positive z direction. So the direction of the magnetic field will be along the positive z direction. Okay, so this is how you can apply. This is very simple example, but there can be many complicated problems. Well, I'll be discussing the numerical problems on this chapter in the next class up to Savarts Law. That time you will realize there may be very simple problem as well as very complicated problem. asked in the exam. Okay, now we'll just move on to the application part of it. Oh, okay, just a minute. So we have to apply this by Savarts law to calculate the magnetic field for a current carrying loop. You can see that. Okay, circular current carrying loop. You can see the figure. So circular current carrying loop in the sense when your wire. So if this is a wire, this is not called a loop. When both the ends are actually meeting to each other and forming a closed path, then it is called a loop. Okay, so any shape of loop can happen. Okay, this is a circular and geometry. Okay, that means we can apply some certain geometry in this. So you look here, we have to calculate the magnetic field on the axis of this circular. See, on the axis means I have kept this circular loop in the YZ plane. If you look it carefully, so this is suppose my, so you look, this is in the YZ plane. This is a Y and this is Z. So this is in the, this just standing on the YZ plane vertically. Okay, this is Y and this is Z, which you can see from here also. Okay, it is in the YZ plane. YZ plane, I'll just draw the whole coordinate system, then you can find out. So this is Y and this is Z. So this, in this plane it is actually in this plane like this. Okay, YZ plane. And it is, see, the circular loop is placed such that the center of the circle is actually at the origin. At the origin. So I can write, I can keep this circular loop in the YZ plane in such a way that center of the loop is actually circle is coinciding with the origin. So this is what has been done here. And a steady current that I have already explained what do you mean by steady current, which doesn't change with time and space as well. So steady current is flowing, and see, always we become little confused with the word axis, etc. So in this case, axis means if you have a, if you know, like you have a, if you have a bicycle, you know that you have the wheel and the axle is passing through the center. Actually, that is, and around that the circular wheel is rotating. So that's why it is called axis. So that means if you just pass through a metal shaft through the center of this loop, then it is called axis of the loop. That means this. So any point, I am just, now I have a project to calculate the magnetic field applying by Savarts law on, at any point, suppose P1, P2, P3, at any point at certain distance from the center of the loop, and these are actually called axial points. These are called axial points. So you have to find out the magnetic field on the axis of the circular loop. So this is our project now. So what we'll do, I know what I know by Savarts law in the vectorial form or vector form, I dl cross r by r cube. All right. So this is my by Savarts law. Now let us see how we can apply this by Savarts law to calculate the magnetic field due to this circular loop at any point P on the axis of this loop. Okay. So suppose the radius of this circular loop is r, capital R. You can see that, and the point is P, where I have to calculate the magnetic field, which is at x distance from the center or the origin of the center of the loop. Okay, from the center of the loop at x distance, I have taken this point P, and let us suppose as this, since this loop is kept in the YZ plane, the axis is actually x axis. Okay, the axis of this loop, okay, axis of this loop is suppose x axis. Okay. Now, as I told, you have to first consider a current element, small current element, and first calculate the magnetic field for such elements. Okay, until you cover the whole length of the wire, or whole length of the loop. Then what you can do, you can take the value of, suppose I can take here one loop here, sorry, current element here. Look, this is a current element. Okay, I can take another current element here, another one here. So until if you cover the whole periphery of the circular loop. You take small element, calculate the magnetic field for each element, and then you can sum them up to get the whole, get the magnetic field, total magnetic field at this particular point due to the whole loop. Okay. So how to do that? So I just take this loop. You look, if I take any element and radius vector, that means the the line joining the point where I am calculating the magnetic field, suppose this is P, and this element, they will be always, since this is a circular loop, they will be always actually perpendicular to each other. Okay, they will be always perpendicular to each other. Okay, they will be always perpendicular to each other, because the current is in this direction like this. It will be along the tangent. So the direction for this circular loop, the direction for this current element for a circular loop will be always at the along the tangent, and radius vector is always perpendicular to the tangent. Okay, so that's why the angle between this ideal and R, if this is R, here is shown, you can see in the figure. So that angle will be always 90 degree. So this I can write then dB is equal to I dl by R square, and this is sine 90 degree. That means this is the thing. Okay, and see this R I can write as actually R I can write as, or R square I can write as R square plus x square from Pythagoras theorem. So this I can just take this as a triangle and write this one. Okay, now I have got the magnitude. Okay, but not the final one, obviously. Now I have to find out what is the direction of the magnetic field. Look, I know the magnetic field will be in the plane perpendicular to the plane containing this dl and r, ideal and r. So look, if you apply the thumb rule for cross product, see this is the direction for this, and you just apply just like shown here. If you apply this thumb rule, so this is this is the direction. Suppose this is your a vector, this is your b vector, and if you apply this thumb rule, that means you stretch your four fingers like this along this direction, and then curl them, as you can see here, towards R. You look, the direction of the magnetic field will be exactly this. This is the direction of the magnetic field. You can demonstrate by yourself. If you are not getting, you try again and again to demonstrate it, this thumb rule, then you will look that you will get the direction of the magnetic field as this one. Okay, so now look, I have got the direction of the magnetic field as this one, which is making an angle theta with the x-axis. So this is the total magnetic field which I get for this particular element, and it is making an angle theta with the x-axis. So what I can do, I can just break into components. So I can write dbx, which is along the x-axis, which is actually db cos of theta. Okay, the db is this one. Okay, this is this one. I have got a magnitude. This is cos theta. And see, in the perpendicular direction, I can write dB perpendicular as dB sine theta. I hope you people will agree with me. Now, if I take exactly opposite side, if I take another element exactly in the opposite side, look what I will get. So I'll get the total magnetic field if you apply your right hand thumb rule for this element. For this element, suppose this is also R by symmetry. Okay. So you look, this magnetic field, total magnetic field for this DL element will be in this direction. So if you take, so this angle by symmetry, this also will be theta. So which is making angle with the x-axis. So this also will be theta by symmetry. So look, this angle also will be theta. So it also will make an angle theta with the x-axis. This will be theta. So now you have to actually break the component of this and see in which direction what component you get. So this one, you look, this is actually d perpendicular for this length, this element. Okay, and which is exactly equal in magnitude with this. Okay, so this one and this one will cancel each other, and the cos theta component will actually be added to this. Okay, dB cos theta again here. Okay, understand, right? So as you can see, if you take to symmetric this DL like element everywhere, you will see the perpendicular component will cancel each other for any element you take, but symmetrically opposite you have to take. Symmetrically opposite if you take, you look that the perpendicular component will cancel each other. What remains is the cos theta component. So I can add these two up and get the total magnetic field for all of them. Okay, look, the calculation I'll show you in your book now. So I'll get the cos theta component. So as I said, I'm just calculating for one element itself, but I have taken the other element opposite direction to show you that the perpendicular component will be cancelled by each other and all cos theta component will be added up. So now I'm just sticking to only one element and doing the calculation. Let us see here what we can learn from here. So I can write, see, the total magnetic field will be actually okay, I just go to presentation itself. So the total magnetic field for, or the effective magnetic field for particular that element, this element will be in the along the x direction. And in fact, if you take any symmetric elements like that, you will get this component itself. So I just take only one now and then I'll sum for all of them. So you'll get I dl by r square, okay, r square into uh, cos of theta, okay, cos of theta. All right. So this r square, as I have told you, that from this geometry, so this is r, this is x, this is point P, and this is your capital R. So from here I can write it. Okay, I can write r square is equal to capital R square plus x square. So this I can write. Now I have to see what is the value of cos theta. So to know that, we have to go here. Okay, we have to go here. Okay, I think I'll delete everything what I have here. Okay, now let us see what is the value of cos theta. What I can write about cos theta. So look, if this is theta, so what is the angle of this? Because cos theta I have to write in terms of our known term, this one, and this one. In terms of these three parameters I have to write. Okay. So how can I write that? So I have to then find out what is this value. Suppose this angle is x. So what you can write? So this x, the x plus. So this angle up to this, they are 90-degree perpendicular to each other, because the IL cross IL and R and dB, the magnetic field, they will be all like they will be mutually perpendicular to each other. So that's why this is R vector, right? This is the radius vector. This is the total magnetic field for this element. So they will be perpendicular to each other. So I can write this as 90 degree plus this angle. Okay, up to this 90 degree, and this is theta as you see. So this I can write as 180 degree. Do you agree with me? So from here I have started, this is x, so which I have to know, and this is 90 degree from R vector to B dB, and this part is again theta. So I have written these things, and altogether this will be 180 degree. So what is the value for this x? This will be 90 minus theta. 90 degree minus theta. Okay. Look what I can write as cos theta here. See, if I write sine of 90 degree minus theta, so this will be actually cos theta, right? So from this geometry, look, from this geometry, I can this I'll treat as the radius, I'll be treating as perpendicular, this as hypotenuse, this is base. So I can write cos theta means, see this for this actually this is 90 minus theta, 90 minus theta. So I can write sine of 90 minus theta, which is cos theta, that is equal to R by small r. Okay, R by small r. What is small r? Then R by, this is R square. So this small r is actually from Pythagoras rule. I can write like this. Okay. So look what I can write here. Total magnetic field, see, in place of cos theta and in place of other two, I'll write. So okay, I'll go to a fresh page. Okay, look, so what I get, dbx along the x direction, I dl, which I already had, and then cos theta in place of cos theta, so I'll write what I had now, this I have now. So I can just replace this value, I dl, cos theta means r by what we have got, this is actually r square plus x square, and this we have got r square plus x square whole to the power half. Okay, a root over this. Okay, so this is what we have got. Now look, if I write this, this is x square whole to the power 3 by 2. Now if I want to calculate the magnetic field for the whole loop, then I can take all symmetrically opposite sides. Okay, anything you take like this, you'll get all dbx and sum them up. Okay, just take the summation. Summation means your FC r is fixed, x is fixed. So what you have to take summation here, you can take the summation of, so summation of db x means the I is a steady current. So this, you have to take the summation of this alone, and you have got r by, this is x square plus r square whole to the power 3 by 2. Okay, so this is what we have got. Okay, obviously one thing I have forgotten to tell you, right, that is mu 0 by 4 pi, that is the proportional constant I would have got if I just, so I think whole, in the whole discussion I have just missed out that. You people should forgive me, and then you should, yeah, you should excuse me for this. Okay, you write this, this is the original formula, so from the Savarts law you can write all the way, and look what I get. So you will be mu 0 by 4 pi, you will get here, and this is the whole part, so mu 0 by 4 pi here. If you write, and the summation over this actually will be 2 pi r. Okay, 2 pi r. You take small length and then add them all, then you get dl as the periphery 2 pi r. Okay, so if you just put this 2 pi r over here, look what I get. This is 2 pi r. So this is I and this. So 4 pi and 2 pi, I can just strike them out. Okay. So what I get is actually mu 0 by 2 into I into r square divided by this factor x square whole to the power 3 by 2. Okay. This is the one. Now this actually this total magnetic field will be along the x direction, along, this is b along x direction, along the direction of the axis itself. Okay, so from here, using this you can find out the magnetic field. Okay, at any point of the axis. So this was my project. Now look, if sometime they will give you a loop and find out, they will ask you to find out. Okay, so yeah, so here the total b will be, so I have got b is equal to mu 0 I by 2 here, sorry 2, and then r square by this vector. Okay, whole to the power 3 by 2. Okay, now look, they will ask you to find out magnetic field at the center, at O, or the center. So how to find out? Then you have to put x is equal to 0. So if you put x is equal to 0, you will get the magnetic field at the center. How you get? Look here, mu 0 I r square, here it will be 2, and this is 0 means this will be actually, look, this will be r cube. Okay, so 1 r gets cancelled with this, so finally you will get mu 0 I by 2r. So this is at the center. Okay, this is at the center. So this is how you will be able to find out the magnetic field at any point on the axis. Now look, for a loop, what is the direction of the magnetic field? So this is another rule which is called grip rule. Grip rule, right hand grip rule, to find out the magnetic field for a direction of the magnetic field for a loop. Okay, I'll take another 2 minutes, another 2-3 minutes to finish this. Right hand grip rule. What is right hand grip rule? If you see, as you can see from this figure itself, if you grip means if you just hold the wire with your 4 fingers in such a way that the tip of your fingers are directing the current direction, okay, then your thumb will give the direction of the magnetic field. So that's why, see, magnetic field lines for a loop you have to write in this way, just by seeing the current direction. If the current direction is opposite, then see, if I write the current direction is like this, so magnetic field lines will be coming from top to bottom like this. Okay, and see, this magnetic field lines actually forms a closed loop. Magnetic field lines, whenever you draw, you will see you have to draw a closed loop. See, this is the magnetic field lines. They form a closed loop, and each current carrying loop can act as a dipole, magnetic dipole. So suppose a bar magnet, you have both north pole and south pole. A current carrying loop also acts as a north and south pole. Actually, they also have north and south pole and act as a magnetic dipole. We'll learn that in the later section. Okay, so it also acts as a bar magnet. How? So which direction is the north direction you look? So in this case, since the magnetic field lines are seeming to be coming out from the top of this loop, so this part, this side, top of the top surface or top faces of the loop. Okay, this top face will be treated as north, and bottom face will be treated as south, because if you draw the magnetic field line, you have to draw like this, isn't it, for a bar magnet? I hope you have learned somewhat in your previous classes also. and like this closed loop. So magnetic field lines always emits from the north pole and enters to the south pole. So that's why this side for this loop will be treated as north pole, and this bottom of the loop will be treated as south pole. So that's why each current carrying loop can act as a bar magnet, and it is called, and you know, like you have okay, so this bar magnet, each loop will be acting as a magnetic dipole also, magnetic dipole, and magnetic dipole moment will be actually defined as I into A, current into area of the loop. So this will be denoted by small m, capital M, sometime mu also. Okay. So these things again we'll learn, like what is magnetic dipole and all, dipole moments, etc. We'll be learning in the later section. So what I wanted to tell you here is the direction of the magnetic field for a current carrying loop. How to find out? You have to grip the loop with your right hand, like 4 fingers of the right hand, uh, directing the tips. So the tips will be directing the direction of the current, and then your thumb will give the direction of the magnetic field lines. Okay. Okay. So that way you can find out like from which place the magnetic field lines are coming out and through which it is entering. So according to that, you can point out which side is north and which side is south pole. Okay. This is how each magnetic loop will be acting as a source of magnetic field. Source of magnetic field. Each current carrying loop will act as a source of magnetic field, or in any magnetic material there will be intrinsic magnetic dipole. Okay, intrinsic magnetic dipole, just like your electric dipole, which will create magnetic field. In case of magnetism, there is no monopole. There is no monopole in the sense there is no single magnetic charge kind of that. You have either current loop or intrinsic magnetic dipole. That means you have both north and south pole for a single unit, and that unit is the source for magnetic field. Okay. So I think with this I'll stop student class, and I hope you people are all understanding the concept. If you are not understanding, please read the text and listen my lectures again. And still, if you have some doubts, uh, always I'm open to discuss with the people to clear your doubts. And in the next class, what I'll do, I'll take few examples like from your board exam, previous board exams, also from uh, previous competitive exam, and then I'll see whether you people are able to apply this Savarts Law and other things, magnetic forces and uh, drawing trajectory, etc. Those are very important, which I have already covered. So with this, actually, I'll stop this class for today. See you guys on Wednesday. So yeah.